All right, in this video, we're going to pick up where we left off with our prerequisite review, and we're going to look at our second major topic in our prerequisite review, which is going to be geometry and trigonometry. We're actually going to start off first, though, with a review of linear functions and of graphing in general. So a linear function is going to be in the form of y equals mx plus b, where m is our slope and b is our y-intercept. Our y-intercept is actually a point on the graph 0, b. M is given by our change in y over our change in x. And we're going to write that in calculus as delta y over delta x. We're going to use the Greek letter delta to stand for this change in here. This is also the same thing. It doesn't matter which way you subtract. It just matters that the ones are together and the twos are together. The y's are on top and the x's are on the bottom, but we usually do y2 minus y1 over x2 minus x1 is usually what we do. So let's give an example here where our m is going to be a -3 and our b is going to be a +3. So that would make our equation y equals a -3x plus 3. And we want to graph that linear function. So we're going to start with the y-intercept of 3. And then we're going to use a slope to come down 3 and right 1. That gives us the point 0, 3. And that gives us the point 1, 0. This is our y-intercept. This is our x-intercept. We're going to connect the dots here. And that's the best that I can do without a actual graphing utility here. To write point slope form of the line, which is going to be extremely important in calculus. That's going to be y minus y1 is equal to m times the quantity x minus x1. And let's give a point here on the graph like x1, y1 is 0, 3. Using that y-intercept again, we're going to get the same line here. Let's show you that if we had the slope of -3 for this, we would come up with the same answer for the linear equation. So y minus 3 is equal to m times x minus 0. Y minus 3 equals -3x. Y is equal to -3x plus 3. Right? For geometry and trigonometry, we're going to just remember the equation of a circle. That should be something that is in your even pre-calculus knowledge here. And this is actually more generically x minus h squared plus y minus k squared is equal to r squared, where our center is at hk. And our radius is r. So if you remember, ellipses were very similar, but they had a major axis and a minor axis. And we had x minus h squared over a squared plus y minus k squared over b squared is equal to 1. And they were kind of, if a was greater than b, then our major axis was in the x direction. And if b was greater than a, then our major axis was in the y direction, and so on. But there's plenty of that, again, in our pre-calculus review videos that are already up. I want to move on here and talk about SOHCAHTOA to review our trigonometry. That means the sine of an angle is equal to the opposite over the hypotenuse. And if we have a angle in standard position here with this in X, Y, and R, and this is going to be Y over R, our cosine of theta is going to be adjacent over hypotenuse. If we look at in standard position here, that's going to give me X over R, and our tan theta is going to be our opposite over adjacent. And if we look at that in standard position, that's Y over X, which looks strangely like our slope, right? So our tangent of our angle there is related to our slope here in trigonometry. We have reciprocals of these things as well. So cosecant of the angle is 1 over the sine of the angle is equal to the hypotenuse over the opposite is equal to R over Y. Secant of the angle is 1 over the cosine of the angle, and as the hypotenuse over the adjacent, and as R over X. And cotangent of the angle is 1 over tangent of the angle is equal to adjacent over opposite is equal to X over Y. All 6 trig functions are positive in quadrant 1. Sine and its reciprocal, cosecant, are positive in quadrant 2. Tangent and its reciprocal, cotangent, are positive in quadrant 3. Cosine and its reciprocal, secant, are positive in quadrant 4. All other functions that are in a quadrant where I've identified 1 and its reciprocal that are positive, all the other ones are negative. So in quadrant 2, where sine and cosecant are positive, that means that cosine, secant, tangent, and cotangent are all negative. If this one says tangent and cotangent are positive, that means sine, cosecant, cosine, and secant are all negative, and so on. So you should know these special angles, both in degrees and radians, and you should know their sine and cosine values off of the unit circle from pre-calculus. And tangent is going to be sine over cosine. That's one of your special quotient identities there. But the point on the unit circle here is going to be the cosine value and the sine value, and that has to do with the fact that X is equal to R cosine theta and Y is equal to R sine theta in polar coordinates. And if R equals 1, which is our unit circle, if R equals 1, then and only then does X equal cosine theta and Y equals sine theta. So let's evaluate sine of 4 pi over 3 using our unit circle. 4 pi over 3 is right here, and the sine value is right there. So sine of 4 pi over 3 is equal to a negative root 3 over 2. Remember that positive angles are going to be measured counterclockwise from the positive x-axis. Negative angles are going to be measured clockwise from the positive x-axis. Cosine of 4 pi over 3 is going to be a negative 1/2. So the reference angle is going to be pi over 3 here, which is up here, but we're in quadrant 3, so it's negative and negative. That's another way that you could do that. Let's go ahead and let's look at some other examples here. If we wanted to find angles that are, say, coterminal, we might want to say, what's 4 pi over 3 plus 2 pi? That's over 1. Multiply this by 3 over 3. 4 pi plus 6 pi over 3 is 10 pi over 3, and they're going to land at the same place here on the unit circle. Just one of them I went around like this. The other one I went all the way around and then back around and landed at the same place. So they're going to have the same sine and cosine values if they're coterminal. Let's go ahead and let's look at the catalog of functions. I'm going to come back to my graphs that are over here that are pretty for sine, cosine, and tangent. So the sine function is going to be, it's important to know that this is an odd function. It has origin symmetry. We didn't really mention that up in the other functions up here, but I guess I should tell you that this one is odd, this one is even, this one is odd, this one is neither, this one is odd, this one is odd, and this one is even. If they're even, they have y-axis symmetry. If they're odd, they have origin symmetry. This one is even. These are neither. Right? And this is neither. Right. Cosine is going to be an even function, meaning it has y-axis symmetry. And let's talk about the waves here. So what's different about sine, cosine, so on, they're what we call periodic functions. So they come back to the same place over and over again like a wave. That's why we can represent them like a circle, where we keep taking revolutions around the circle. Or we can look at them like waves. It's better to look like that. Look at them as waves many times with oscillations in physics, especially if we're talking about how far did we travel, things like that. But the domain here of the sine function is negative infinity to infinity. Notice that it's bounded here. It's restricted between y equals -1 and y equals 1. It's going to be important when we restrict this later to know that the restricted capital SIN function, capital SIN of x is restricted to have a domain of -pi/2 to pi/2, and its range is also -1 to 1. We want to get all the output values possible, but only get it one time. It's going to be 1 to 1. Capital cosine of x will have a domain of 0 to pi, and we'll again have a range of -1 to 1. Again, these capital sine and capital cosine only matter to us when we're looking to find inverse functions later. So we'll pick that up in just a second. Capital T tangent of x that would be restricted is going to be this first period here from -pi/2 to pi/2, and actually -pi/2 to pi/2 are asymptotes. They're not going to be included, but we can get answers for the inverse function to be that, depending on if we're going to positive infinity or negative infinity here. The range here is going to go from negative infinity to positive infinity. Your domain is going to be everything for tangent. It can be everything other than the other than the multiples of pi over 2. Let's say the odd multiples of pi over 2, like that. It's okay if k is an even number because then you get one of these zeros here, but it can't be an odd multiple of pi over 2. So the way to actually write that is 2k plus 1 pi over 2. That's what our actual restriction is here. Again, I got this from a free online textbook, so it needs a little correction every once in a while. And the secant function is going to be based off of cosine, where cosine had zeros. We're going to have asymptotes. So zeros at negative pi over 2 and pi over 2 and 3 pi over 2 and so on. And again, the zeros of cosine were the asymptotes of tangent. So we have the same thing here, where the domain here, it can't be an odd multiple of pi over 2. And notice the range here is that it goes from negative infinity to negative 1 included, and from 1 included to positive infinity. We'll come back and we'll talk about these inverse trig functions in a minute. But I do want to talk about what the graph of cotangent looks like. That was not there. So it looks like this. And it's going to have cosine over sine. So it has asymptotes at 0 at all the multiples of pi. And the things that were asymptotes before for tangent are now the zeros. And where tangent was increasing, this is decreasing, like this, because we took the reciprocal. And so on. It looks like that. So that's the only one that I didn't have a graph for. You can apply all the shifting and scaling rules to these trig functions as well, but just make sure that you know that these functions are periodic, and you also can't get the b part out that's with the x on the inside. You can't get it outside like you can on a lot of the elementary functions. So because they're periodic, if I add or subtract 2 pi, the period, to sine and cosine, you get the original function. Remember, the period of tangent and cotangent is just pi. They're based off of the slope. So you come back to the same line every pi radians. That's why their period is pi. Secant and cosecant have a period of 2 pi as well. So let's go ahead now and let's think about the inverse trig functions for a second. And this is what I was just talking about, that we want to first think about what capital S sine is going to look like. And we restrict that so that it's just this piece of the graph here, from negative pi over 2, negative 1, to pi over 2, 1. And then when we do that, we can find the inverse reflecting it over the line y equals x. But right now, the domain of this is negative pi over 2 to pi over 2, and the range is negative 1 to 1. So when we find the inverse over here, f inverse is going to be sine inverse of x, and it's going to have a domain of negative 1 to 1 and a range of negative pi over 2 to pi over 2. Note that this inverse symbol here, this is inverse, not reciprocal. Don't use that for reciprocal notation. So another way to write that to avoid confusion is to write arc sine like that. And I'll try as much as I can to remember to write arc sine, but your calculator is going to use the second sine function, will be arc sine like this. For cosine, we're going to restrict it to be this portion of the graph right here that goes between 0, 1 and pi negative 1. So our domain of our capital C cosine is from 0 to pi, and our range is going to be negative 1 to 1. And that means that our inverse function, arc cosine, which is related to this one, will have a domain of negative 1 to 1 and a range of 0 to pi. And we'll write that also as arc cosine of x, arc cos, to avoid any confusion that this is an inverse function notation. It's f inverse of x. All right, tangent. We're going to capital T tangent, restrict it. It's going to be between negative pi over 2 and pi over 2. And it's just this first period here, where my domain is going to be negative pi over 2 to pi over 2. Even though it's undefined at those places, my range is going to be negative infinity to infinity. So my inverse function here is going to be arc tangent of x, or arc tan of x like this, and it has a domain of negative infinity to infinity and a range of I'm really going to put these in parentheses, negative pi over 2 to pi over 2. It gets close to those asymptotes. I'll show you what this one looks like. This one's kind of interesting because it's one of the only graphs that you're going to know that has a double horizontal asymptote in it. It's going to look like this. This inverse function here is going to, it's increasing range goes from 0 to pi. I'll show you what those look like here. So the inverse sine function looks like this. The inverse cosine function looks like this. I already showed you what the inverse tangent function looks like that. So let's go ahead and evaluate the following. Where on the unit circle, or just where in general, does the sine have a value of root 2 over 2? So what I'm asking here is if arc sine of, this is always going to equal an angle. sine of what angle equals √2/2? Well, remember arcsine is restricted. There should only be one answer here. So we should be in quadrant 1 since we have a positive sine value. So there should be pi/4. Whereas arctangent 1, tangent has a positive value. So we're in quadrant 1. We're also at pi/4 there. Arctangent is going to be negative. That's going to put me in quadrant 4. It's going to be a negative angle. So that's going to be a negative pi/4. So we have to stay between negative pi/2 and pi/2 for arctangent and arcsine. So that means that we have to give negative angle values there. All right, that's going to be it for this video, and this wraps up our pre-calculus review. We'll come back next time and we will start talking about our calculus topics with the idea of the limit next time. See you for the next video.